I thank Rakesh for inviting me, and it's a great place. And it so happened that this is my third visit to Jaipur LNMIIT, and I'm very happy to be here again and again, and enjoy this place. So let's hope something interesting is given in this program. So I've decided to talk about some work which I've not yet, we have finished more or less, uh, but it's being written, the draft. And the draft, as you know, will take several days of correcting, shaping, etc. So maybe within a month, we will be able to put it up in the archive. But I'll give you the details which looks quite confident. And there is no tension. I don't have a tension, and Hubble also doesn't have a tension. Okay. First, so what is it I'm going to talk about? Since Rakesh told me that make sure that students also benefit, at least for half an hour, I will try to make it they benefit at least 1 hour. And the plan is going to be fairly elementary. I will explain Hubble tension, and then I will tell about what are the problems and how this Hubble constant is measured, found experimentally. And there are two places where the measurements are found. And the tension is because the two values which you get by the two methods are differing by about 10% or 78%. And there is no way to reconcile them as per the earlier thing, because there is some theoretical understanding, there is some experimental measurement. Either experimental measurement errors are there, theoretical understanding probably may change the theory of how it is done, and it may improve it, and that can happen. So I'm going to talk about what is called Chandrasekhar's limit in white dwarf, which we all know. There is this, any white dwarf cannot have a mass which is greater than 1.4 solar masses. Unfortunately, there are now evidences, possible evidences, that there are some candidates whose mass can be more than that. And there were attempts to do this kind of a thing earlier, because Chandrasekhar did with white dwarf, the stars, which are rotationally invariant. So they put some spin and then found the mass increased from 1.4 to 1.42 or 43. Nothing much happened. There are some people who did some magnetic field. The star itself has magnetic field, magnet, and that improved it by 1.6 or something like that. So this kind of analysis which I'm doing as to improve it, will improve it to something like 2.2 to 2.4 solar masses. And I will explain why it is happening. So I will talk about something on that, primer on white dwarf and Chandrasekhar limit, followed by what is called the fuzzy sphere. This is the only mathematics I'm going to use to some extent, and I will make it as simple as possible. Then I will talk about squashed fuzzy sphere. That is what I'm going to utilize in this model, and there is a reason for it. And then after that, I will go to this what is called type 1a supernova, which is related to the white dwarf issue, which I talked about, which is what is used to find the velocity or the distance and velocity relation for the galaxies, and one other thing. So I will talk about it. And the crucial thing is what is called the trip formula and nickel roll. This is the real experimental thing. The data is taken from whatever is from papers which experimentalists have given, and then we have to utilize and then make some analysis based on that to make the claim. And then I will finally give some result based on this. This is basically my program. Okay. So what is Hubble tension? There are two measurements of Hubble constant, and I'll tell what is Hubble constant also. For the moment you take that thing, one is a local in the neighborhood of our galaxy, and another is based on the effect of cosmic expansion of the CMB. There are two numbers which you get. One of them is 74 kilometers per second per megaparsec. The numbers are exactly what is there. Typical, I have approximated, it's from 73.8 or something like that. For our purpose, this is good enough. The second is 67 kilometers per second per megaparsec. This is the, what are these numbers? I will explain. And point is, these two values are two different sets of experiments people measure, and each one has their own theory. And based on that, they have come to the conclusion, they found that they cannot reconcile these two numbers. And that what people call as a tension.
What is the errors?
The errors are within which cannot explain the difference. The errors are there. 73. Yeah, that's a kind of numbers. But any of the errors I will give, it is there. Errors cannot explain the differences for whatever it is. So the experimental errors. The theory is another one. The theory itself may require some changes, which a lot of people, in fact, the number of papers after this issues came up the last maybe a decade or 2 decades is more than the number of stars in our galaxy. Don't worry about it. So we will explain briefly Hubble constant, local measurement using type 1a supernova, and Chandrasekhar limit. This is what I'm going to explain more and more. I will not touch the CMB part of it. I will just leave it as such, but I'll tell what is happening with respect to this. Okay. A possible resolution could be to relook at Chandrasekhar limit due to statistics change. I'll tell you why it is so. We explain the source of this and a model to implement such a change. It's only a model. So it says that model with this kind of a thing can enhance that number, and which is crucial. And that model is using what is called the fuzzy geometry and what we call super Chandra limit. The same thing can be done for neutron stars, which I will not touch. My collaborators have used it because I'm not a regular astrophysicist kind of cosmology person. So these things we started talking because they were interested in my work. That is how it happened. So I will revisit the Hubble constant using type 1a supernova. I will tell you what is type 1a supernova in detail, and the role of super Chandrasekhar white dwarf, which plays a role in this. This is what is the program. Okay, Hubble constant brief history. So the question is, our universe expands, which we all know for more than 70 years we have been learning about it, at a speed proportional to the distance from us, and that is that relation V is equal to h naught d, and h naught is what we call as the Hubble constant. And it is called Hubble's law because since it was discovered by Landmark. So anyhow, what happens is this. LNMIIT proved a theoretical framework for this in general relativity. Hubble confirmed again by his observation, but actually Landmark gave 3 years before LNMIIT and 5 years before Hubble this kind of a thing, data and details, and his numbers were much better than Hubble himself. And of course, Hubble was a much more wider set of new numbers were also given, but this is the idea. And in 1952, Walter Baade made the detailed analysis and announced this as a law, that Hubble's law as a statement, this law that it is proportional to the distance, was made at that time. And but only thing is the numbers were between 50 to 90 kilometers per second per megaparsec at that time. It's quite varying. In 94, NASA, a key project, gave a value from the recession velocity of Virgo, and that is the numbers which they were giving. These are all old stories. And in 1995, Rees et al., after analyzing the type 1a supernova, gave light curves for luminosity, something like 67 plus or minus 7. Finally, this is the other result which was there. These are, many of them are incorrect and revised much later. So there are two quantities to be measured. You have to measure two quantities to get the expansion rate. The recession velocity of the galaxy V is measured. The speed with which it is going is to some extent easier to measure. You can measure the redshift of the spectrum which is there, and that redshift will give you the emitted radiation of the stars in the core of the galaxies, and the velocity can in principle be measured to some reasonable accuracy. This thing. The whole problem is, what is the distance of the galaxy or whatever stars there in this thing, and how do we measure it? It's not like you sit and measure using parallax method, etc., because the distances which we are talking about are in megaparsecs and million lakhs of parsec, etc. That is the kind of distances, and the parallax thing cannot be used. So we need a better way of finding out what is the distance of those objects from us. That is what is the thing, and that is measured using what is called the standard candle. And the role of standard candle is what is played by Chandrasekhar limit. One of the things. Okay, and first, this is a very brief statement. I will not touch about this. CMB and expansion of the universe by assuming what is known as the standard model of cosmology, what now people use. And maybe there will be changes, modifications, etc. in it. But general lambda CDM is taken as some kind of a background on which you play with. We can infer the expansion rate from the sizes of the largest fluctuations seen in the cosmic microwave background. A higher expansion rate would imply a smaller characteristic size of the fluctuations, and vice versa. The Planck collaboration measured the expansion rate this way and determined it to be 67.4 plus or minus 0.5 kilometer per second. This expectation of the Hubble constant does not match with local measurements, which are confirmed again by JW recently, JWST thing which was sent also, which is about 73 or 74 kilometers per second per megaparsec. The standard candle. So what is the standard candle? If you know the intrinsic luminosity of an object in the galaxy, maybe a star or something like that, and measure the apparent luminosity here at this place, we will be able to find the distance, provided we know what is emitted there exactly and what is received here by us. We will use this formula. LA is Li by 4 pi d square. It's an inverse square thing which is there. So if you know both LA and Li, we can find out this distance, and that is what is generally used. So Hubble used, there are two things. One is called Cepheid variable. I will not talk much about it because it was not, there are a lot of problems with that also. And for the intrinsic luminosity and redshift of the goal. So this is what was done by Hubble. So a Cepheid variable is a type of variable, star, that pulsates. Okay, it pulsates, the luminosity changes at some rate. So it varying in both diameter and temperature. It changes its brightness with a well-defined stable period and amplitude. We don't have a proper theory for that to talk about it. They are astrophysical benchmarks for measuring galactic. So what they know is empirical result. And they know that the relationship between period and luminosity, and it is proportional to that. The direct relationship exists between Cepheid variable's luminosity and its pulsation period. This is what was the case. So if you know that thing, then you need that proportionality constant. If you know that this is a law, you don't have a proper theory to why it is so. But if you take that, then you can take a very, very nearby star, Cepheid variable, very close, which you can measure by some kind of parallax method. If from there you know the distance, then from there you can find the proportionality constant, and you can apply that constant to other things. So this is what was assumed in this thing, and they made some kind of arrangements. So this is the kind of graph which they had for the period luminosity relation for the Cepheids, this distances, etc. thing, but it has several problems, this thing, because first of all, they are assuming that proportionality constant does not change with distance, number one. So, and they don't have a proper theory to even start with. So I will not talk about this, and I don't understand it also. I am not going into that. Okay. So this is my main thing, type 1a supernova. Type 1a supernova is a binary system where one or both stars are white dwarf, first of all. If a white dwarf gradually accretes mass from a binary companion or merges with a second white dwarf, the expectation is that white dwarf's core will reach the ignition temperature of carbon fusion. Again, it will start the nuclear fusion. When it becomes a Chandrasekhar mass when it reaches that kind of a mass. Within a few seconds of initiation of nuclear fusion, a large fraction of the matter in the white dwarf explodes and releases enough energy, which is of the order of 10 power 44 joules, and that is the amount of energy that will be released. And that is the benchmark of that kind of a thing, if that is the case. So since carbon oxygen white dwarf, the white dwarf which is considered is usually carbon oxygen core, is limited in mass to the Chandrasekhar limit of 1.4 solar masses, they reignite and trigger supernova. This is what is happening. It has a constant peak luminosity and it is used as a standard candle. Peak luminosity constant is due to the critical Chandrasekhar mass. So the Chandrasekhar mass plays a crucial role, that is the one which gives you the reason for the peak luminosity. If it is related to that, then we will be using that. Observed luminosity on Earth, which we can do in experiment, is actually experimental measurement. We measure it in the lab, in the observatory, etc. And you compare with the absolute luminosity provides the information about the distance. This is basically the idea. But there are now cases where supernova do cross the Chandrasekhar limit. And one such example is what I have written down. There are at least some 20 such examples are there on which data is available for lesser number of them. The complete data, like what is its content, etc. I will use only subset of them which is available in the literature. So this is basically the point. Okay, given enough time, the white dwarf can accumulate enough mass to make its own mass greater than the Chandrasekhar limit. When this happens, the core of the white dwarf reaches temperatures high enough for fusion of carbon and oxygen, ending up with degenerate star going through the supernova. That's what is the idea. These explosions release a lot of energy and are extremely luminous, and then slowly the luminosity will come down over a period of month or 15 days to 1 month, etc. Now, because they always occur once the white dwarf reaches the limit, the variation in the luminosity is also minimal. It reduces. These variations in the luminosity of supernova 1A can be standardized for standard candles. So this is a type of curve which is there. So what you have is the nickel is formed, radioactive nickel, and also decays to cobalt. And these are the spectrum of these things are the ones which are measured. And then there is a time scale over maybe a month, 15 days for which they observe. And then they find this kind of a curve which is there. Okay. A standard candle is an object whose luminosity is well known and can be used to measure distances. So for that we have to characterize. We have to find some parameters by which we are going to characterize it. And that is the formula which is 3, which says the apparent magnitude is m and capital M is the absolute magnitude, which may be related to the Chandrasekhar limit or whatever is the mass which is responsible. Whereas the apparent magnitude is something which you measure. And they write it in terms of this 5 log 10 d by 10 pc per sec, because it is equivalent to saying that you keep the star at this distance 10 parsec, and what is the luminosity corresponding to that, and then compare it. This is a kind of a standardization. You don't talk about that thing which is living in some hundreds of kilos, 1,000, 1 lakh parsec, etc. You talk about this number. This is what is used. The idea is if the star is kept at 10 parsec from us, what will be the apparent and absolute luminosity? That is a comparison which is done from where some of these calculations are done. Okay. In fact, I had to learn myself how these people find this kind of a thing. It was an experience for myself also. I learned this kind of calculations I've never done in my life. So this is the first time I started doing this. So this is the thing. Now the Chandrasekhar limit is crucial for peak luminosity. Can I violate Chandrasekhar limit? And that's what I'm going to talk about. It is known rotating white dwarf can have mass greater than Chandrasekhar limit. White dwarf with magnetic field can also violate it, but these violations are by small amounts, 1.42 as I said, or 1.6 maximum, that kind of thing. There is Baniprata Mukhopadhyay is there in IISc who has been doing this for the past maybe a decade or so.
These supernovas, are they not associated with neutron stars mostly?
Which one?
The supernovas, type 1 supernova.
Type 1A supernova. Uh, uh, they need not. They're not necessarily associated. They're not associated with neutron stars. Associated with white dwarfs. Okay, type 1A supernova. That's what I say. It's very crucial. There is also type 2 also, which is slightly different. The regular supernova is what you are associating. This type 1A is very special, where this binary nature of a white dwarf along with another white dwarf or another star is required, and it has to accrete that, and that mass has to go in. It may be starting as a very low mass white dwarf, but it is, since it is very close, it will take more and more mass, and it will reach a new stability place and then become a supernova. That's what is happening. Phenomenologically, that's what is happening. Okay, with Bani and his student Surajit Kalitha, I did consider a model about 4 or 5 years back on white dwarf based on non-commutative squash fuzzy sphere. I will explain these words. That is going to be the thing. And we came out with an enhanced limit of 2.4 solar masses. Okay, that is the limit. So this is basically the change which happens. Since it is this kind of a thing, the mass will play, if it is playing a role, we have to revise our own thing. And I must acknowledge here, about 1 year back, I was in ICTP, where Ravi Sheth from Pennsylvania was there. I had discussions with him, and I explained this Super Chandrasekhar mostly as a theoretical work. Then he raised this question, can it, because if this is the case, we can say that type 1A supernova, we have been measuring the distance incorrectly. So we are giving some value for the distance, but actual value for the distance could be larger. If the distance increases and velocity is the same, h0 value will come down. This is basically the way he was trying to tell me, and why don't you check whether it is true or not. This is the discussion we had over a glass of whatever we enjoy. So this is what happened, and that forced me to go into the theory of this type 1A supernova, and we did this work for the past 2 to 3 months, 4 months, and this is the result. Okay. Well, I'll come to that point. I'll give you the numbers also. I'll write down all those things which are there. It type 1A supernova, it is there, and I will give you those numbers. White dwarfs are the most common final stages of stars whose nuclear fusion energy is exhausted. This is what, for the benefit of the students. They have very high interior density. The density is very, very high. You can assume, for example, the whole of sun's mass, sun, which several lakh kilometer radius, is compressed to the size of Earth. Okay, you can assume how much density it will have. That is what is happening. The structure is determined by this degenerate electron gas. I will explain. They have typically mass of the order of 1 solar mass, 1 in the approximate sense, and a radius of approximately 6,000 kilometers. This is the radius, which is the size of the Earth. And this is the typical thing, though density is very, very high, extremely high. The density of the white dwarf is typically 10 power 9 kilograms per meter cube. If you want, if you know the density of water, you can compare it. Electron degeneracy, how is it that kind of a thing is formed? And that is formed due to two things, because there is no nuclear fusion now. There is only electron degeneracy pressure, and there is also the gravitational pull. The electron degeneracy pressure is no two electrons want to be in the same state. They will try to repel. If there are so many electrons are there, they will try to repel and then try to fly apart. Gravity pulls them, and there is a balance, and that balance is reached according to Chandrasekhar by calculations which were done in those days, doing statistical mechanics of Fermi gas and gravity also put in, and equations of motion are written down, statistical mechanics and equations of motion are written down and solved with numerically or minor inputs. They came to the conclusion it is only 1.4 solar mass. So what are the two ingredients? One ingredient is gravitational pull. The second ingredient is Fermi-Dirac statistics. These are the only things that are. Third thing is electron degeneracy. It's an electron which plays a role. So the mass of electron will also come into the picture. So this is what is the thing. Okay. One minute. So the average distance between electrons in the white dwarfs, we can easily estimate. If you take one solar mass and the radius is given, if you know the density, you certain estimate what should be the distance between two electrons. Okay? And that turns out to be of the order of 10 power minus 7 to 10 power minus 8 centimeter. It's typically the size, the two electrons are close by in the sense of atomic radius. That's what is the thing. 10 power minus 8 is of that number. This is much less than the Compton wavelength of electrons. If you know how to compute the Compton wavelength, you simply put h by mc. H, you know the value, mass of electron, you know the value, c is something you can find out and compute it. It will turn out to be, the number is about 10 power minus 10 centimeters. 10 power minus 10 centimeters. It's 1,000 times or 100 times less than that kind of a thing. Compton wavelength is less than this distance. That's what is. So when the inter-electron distances are very high compared to Compton wavelength, so Compton wavelength is something, and if the electrons are far apart, you can easily apply Fermi-Dirac statistics, which means if I exchange two particles, the phase will change by minus. They will be antisymmetric. That's what is the principle which is used in doing your statistical mechanics of ideal Fermi gas. We are not bothered about the Coulomb repulsion, etc., about this. It's only this much. So this is what is done, and this is what was used by Chandrasekhar. The only thing is, earlier calculations were done using non-relativistic statistical mechanics. He used relativistic statistical mechanics in computing the partition function. Okay. In that limit, inter-electron distance, when he reached that 1.4 solar masses, he was coming very close to 1.4 solar mass, comes very close to Compton wavelength itself. So when it is compressed more, if the distance between electrons is more than Compton, is less than Compton wavelength, then it becomes a problem. You have to apply Fermi-Dirac statistics very, very carefully. And the reason is, when you have the two electrons are very, very close to each other, that one electron here sees not one electron there are electron-positron pairs also in that kind of time, length scales. When they are there, when you try to apply the Fermi-Dirac statistics, you have to make sure which one you are going to antisymmetrize, the pairs, etc., which are there. So it is between the thing, etc. So there is a new effective statistics which you have to find out. Effective statistics which you have to apply. So you have to make sure that effective statistics implies there is this new thing which is happening when the density is so high that the distance between two, average distance between electrons is less than the Compton wavelength. Okay, so we essentially modify the effective statistics of electrons. For that, we use a model which is due to non-commutative geometric fuzzy space. I will explain these words separately. Okay, there are two lengths of importance for us. One is 10 power minus 10 centimeters, another is 10 power minus 13 centimeters. What are these lengths? The Compton wavelength of electron, and then the next one is neutron. These are the only things that are there in that place. Compton wavelength of neutrons are of the order of 10 power minus 13 centimeters, and Compton wavelength of electron is 10 power minus 10 centimeters. Now, these are responsible on the average for the formation of white dwarfs, which is of the size of 6,000 kilometers, and the formation of neutron stars, which is of the order of 20 kilometers. The neutron stars, if the mass is so high that it collapses even more than this, then it will go even interior, and then more mass will be accumulated, and it will become a neutron star. And this neutron star has something of the size of less than Jaipur. So this is the kind of size which you have, and 20 kilometers or 10 to 20 kilometers to be precise. The question is, what happens between 6,000 kilometers and 10 kilometers, 20 kilometers? The neutron star things which you want to consider, if you want to consider, you have to take into account other things like QCD and other things, because neutrons will be there, protons will be everything, which we are not going to that kind of scale. We are going to stop between neutron star and white dwarf, whether what happens there. This is basically the idea. That is where the fuzzy geometry, which allows for modification of statistics from Fermi-Dirac's, helps in understanding. So this is the background why I was looking at non-commutative geometry, and I will explain what is that. The basic idea is, in non-commutative geometry, fermions behave less of a fermion, and bosons behave less of a boson. As you know, when you exchange two identical particles, the wave functions are symmetric, which is what bosons are, antisymmetric, which is fermions, which is parameterized by e to the power I theta, where theta is 0 is boson and theta is pi is fermion. If they are the two limits, if it is going to be less of a fermion, so it is going towards the bosonic side, which means that in Fermi-Dirac statistics, if it is different from fermion, which means it is going towards bosonic thing, towards that, the degeneracy pressure will be reduced. If degeneracy pressure is reduced, gravity is more, the gravity is going to pull more and more of that, and the mass can increase. This is basically the idea, and it does. So this is what I'm going to use it. So we all know the sphere. We all know it's very simple. Xi square is equal to r square, where xi is x1 square plus x2 square plus x3 square, is what we call as a sphere, regular sphere, not fuzzy sphere. This is what thing. And xi, xj are commuting coordinates. You can write any function of f and any function of g, you can exchange them without any problem. This is what your regular commutative sphere. That's the meaning of that, in the sense of what Ball described today's morning of non-commutativity. Okay, so the person who started this game of fuzzy sphere was John Mador. He essentially defined fields on the surface of a sphere. On the surface of a sphere, he described a function something like phi of xi, which means phi of x1, x2, x3, or xyz, subjected to the above condition. We have to make sure it is x1 square plus x2 square plus x3 square. So it's only 2 degrees of freedom on the surface of the sphere. Yeah, that's what neutron Compton wavelength is of that type.
You are saying that the physics stage or standard model.
I will say, I'm not going even up to that. I will go beyond electron with Compton wavelength, but maybe about 500, 600 kilometer radius thing. 6,000 to 220 is quite large, so I'm going to reduce that kind of thing. Okay, what is non-commutative fuzzy sphere? So essentially what Ball called as commutative algebra of functions, which essentially means I can define phi of xyz or f of xyz, g of xyz. If I multiply two functions, I can interchange without any problem. That's what is the commutative algebra of functions. Non-commutative fuzzy sphere is defined by xi square is equal to some r square, and xi xj is not commuting. It's like angular momentum. Okay, like jx jy is not 0, it is jz. That kind of a thing with these numbers which are there, some parameter h bar I have put in, and the radius epsilon ijk. The crucial thing is this is the relation which will be there. Here k is a constant and xi become angular momentum generators. So if I want to write a point in this thing, I have to write it as an angular momentum operator, JLI or JI. Okay, then I can always define a matrix function, f of xi, x1, x2, x3. If I write x1 square plus x2 square, if I write it, it will become a matrix. Like that, you can write matrix functions without any problem. But the only thing is those matrix functions will not commute, will no longer commute. They will have this kind of a thing. Huh? Yeah, I'll come to that. That's a parameter which I put in my hand, which I will be using to fit some of the, it is related to our white dwarf mass and other things. Yeah. I kept 1 by r because of some, because xi, xj have the dimensions of L square. So probably to manage with that, I have put it there. Okay, this is a non-commutative algebra of functions, and we do quantum field theory on such spaces. You can think of as you are doing lattice theory on the surface of a fuzzy sphere. You can even think of that. Depending on the value of the j, the number of states will increase, and it will become more and more coarse-grained. When j becomes infinity, you will go towards the commutative sphere. Okay, that is the way. In fact, we thought of that as a lattice formulation on the surface of a sphere, and we did some calculations based on this kind of a thing. This is basically the idea. Well, I'm not at the moment looking at any specific value. Yeah. Yeah, it is in between that. That's a value which I'm going to have, but okay. So the question is, then if you are going to do field theory, then you need what is your Laplacian. Laplacian is p square, pi square. That's what we will write. But here, as you can see, the xi, xj are canonically conjugate kind of a thing. The translation of xj is done by xi. So that's why we call this xi commutator xi with some dot which is there is some function of any function which you write, and that is our Laplacian on this space. And this thing you can even write down the eigenvalues like our spherical harmonics which we wrote. We can write down the spherical harmonics for this, which is essentially ylm theta phi, ylm, where L into L plus 1 are the eigenvalues and ylm are the eigenfunctions, and L goes from 0 to n minus 1 because our matrix is size n, and the m value goes from minus L to plus. These are all known angular momentum results which I borrowed, which people have been doing it. Now, this is the fuzzy sphere, and that is not what I want, because I'm trying to model my white dwarf beyond the Chandrasekhar limit, some kind of a fuzzy sphere. The non-commutativity has to be put in, but when you go to the edge of that white dwarf, it should become commutative, and close to the center, it's non-commutative. So there should be a gradation in the non-commutativity as you go from the center to the thing. And such a model was given by this person Steinacher. He called it as a squashed fuzzy sphere. What he did was take the sphere, just project it to the plane. Okay, that is the way he did. And fuzzy sphere is the configuration where points of a fuzzy sphere are projected to the equatorial planes. If you do that, this is what happens, equation 7, where essentially we replace our x3, because you are squashing it to this thing, replace x3 in terms of x1 and x2, you get that r square minus x1 square minus x2 square. When x1 square and x2 square, these things are reaches the value of the radius, okay? Right hand side becomes 0, it becomes commutative, but it is not commutative otherwise. This is basically the idea. Now, the Laplacian for this is simple. The same kind of the squashed fuzzy sphere Laplacian. It is the same thing with I is equal to 1 and 2, because we have only two variables, x1 and x2. We can write it in terms of theta and phi also. We can write it in terms of theta and phi. And they satisfy this kind of equation. which is not, it is there in Steinacher's paper itself. We have just used these things. So this is the eigenvalues and eigenfunctions of squashed fuzzy sphere, which will model our case. The I is equal to 1, the x3 is not there.
Oh, in the other one,
Then,
so you're explicitly solving for the x3 and plugging it in.
Yeah.
can you remind what is the motivation for considering squash?
Yeah, because we want to model this by first we want to model by some geometry which will produce statistics change, and that is non-commutative geometry. Fuzzy sphere has uniformly on all everywhere, it is the same amount of non-commutative is fixed. Whereas if I squash it by this thing, at the core, very close to the core, the non-commutative is larger, and when you go to the edge, it is there. That is where the density is more. That is what is it. Okay. So this is the thing, and what we don't need the Laplacian. Laplacian I gave as an example. What we need is a Dirac operator because we are dealing with electrons. The Dirac operator is easy to write down. Sigma 1 x1 commutator with that function, x2 commutator with that function, where I have actually put the C also for whatever purpose. I don't even remember why I put it, but doesn't matter. I like C is equal to 1. So sigma I are Pauli matrices. Well, this is the thing. And this is a calculation which you usually ask your student to do it. And they have done. And also it's there in Steinacher's paper also, verify it. In fact, it is turned out that Surajit Kalita, who did this calculation, he found a mistake in Steinacher's paper and wrote to him. And Steinacher agreed with that and then said, yes, you are right. So this is what happened. So this is the thing here. For upspin and downspin, these are the eigenvalues. Energy, PR is the momentum of the electron in the radial direction. This is the thing. And in the above, N is L max plus 1. L tilde is L max minus L. M tilde is L minus M. M prime is L plus M. These are the notations for the eigenvalues which I have given in the previous this paper side. Okay. In the large limit, the energy dispersion relation reduces to this thing. Okay. So the nu is some parameter, M tilde for spin up and M tilde prime, which are already I have given here for spin down electrons. So now I just compare this dispersion relation with Landau quantization due to magnetic field, and that will turn out to be just this thing will be replaced by a critical value for magnetic field, and magnetic field is there. So essentially magnetic field is playing a role in a different way. It is generated. That's what is responsible for the statistics change also. That's there even in quantum Hall effect and other places. Okay. So now equation of state we have to start working out, which means I have to consider this degenerate set of electrons and find out the partition function from where you compute the pressure. And then we have to write down what is called Tolman-Oppenheimer-Volkow equation. The two equations are there and you have to solve it either numerically or as best as possible. Okay, that's what is done, and that is what our results are. Okay.
Why are you singling out a place? That your whiteboard is.
So that choice. See, I'm keeping it that way. The choice is done in such a way because I have the radius. As you go away from the center, the non-commutativity I wanted to reduce towards the edge, and I achieved that by this model.
Isn't the point of
No, yeah, at the end,
observation spherically symmetric object?
that is true, but that choice I can play with any this thing. Finally, it doesn't affect the result. What is affecting the thing is it produces an extra term, and it has this behavior. This is the choice which was made, and it is a model which is giving me the reasonable thing. I could have done with other ways of doing that, but we didn't think of, because this is a model which Steinacher has given already. I can use it. Yes.
What I think you really need is basically a change in the dispersion.
Yeah, that is the
You
part.
just keep it as a one parameter freedom and then
You can do that. You can do that. But our friend Srenakar, you also know him, has done these calculations. So we essentially took that as a model for our purpose. Okay. So this is basically the thing. The partition function is written down here, and this is the result for the partition function. Huh? No, Z is perpendicular to that. Okay, that's it. So this is no, but this Z is a fugacity, e power beta u. Z which is appearing here in this thing. But here that part is taken radial and two angular directions are there. That's all that is used. Radial direction is PR square C square. Other one is this. So we call it, I don't know, I should have put it as PR square. I made a mistake here. Okay. So this calculation is not, you do it as best as possible, and you can work out the Fermi momentum in this case with this spectrum which is worked out. If you have worked out the spectrum, you can find out the Fermi momentum up to which it will go. And that will also be proportional to the density cube, like in Chandrasekhar's case, but the constant is different. The constant of proportionality is different in this case. And the pressure is what you have. This is the change that will be there. The change is essentially fixed by this new parameter, which is coming from the n value which I have fixed, which will tell me what is my fuzzy sphere. Okay, so this is basically the pressure. Okay, so now the TOV equation and limiting mass. Again, this is some serious calculations, which I'm not going to describe. I will only display the equations. So we have worked out the pressure, and we have the relation for the mass and the Tolman, Oppenheimer. This is exactly what is there in Chandrasekhar, except for the definition of our pressure. And essentially, we have to solve this equation. We solve this equation for different values of mass and the parameter nu, and I will only display what is happening in the way in which the limit is obtained. The limit is limiting mass, radius, density. So there is a mass as a function of, as a parameter mass, solar mass, and there is a density in this thing, and another one is the radius of in terms of the kilometers, which was what was used by Chandrasekhar. I'm only more or less playing the same role. Now, for low densities, unlike the previous Chandrasekhar limit, this is the starting point. Okay, for low densities, it starts off, the Chandrasekhar limit is the black one, which is here. It's also we want it to start like that. We want it to start like Chandrasekhar thing. For different values of that parameter nu max, it will tell me what is the spin J value I have to go. We have drawn these curves, and the curve which is giving the best value is, there is that 2.6 or 2.4 here. This is the way in which this curve will go here, and this is the way in which our white dwarf can maximum. Unlike the case of Chandrasekhar's limit, it can exceed that by this kind of amount. The basic principle which we have here is Chandrasekhar limit can be exceeded, and it can be quantified by a new kind of parameter which tells me how much statistics is changed, and it can go of the order of 2.4, 2.5 solar masses. The exact number is irrelevant as of now, because we don't have a way of measuring the mass unless we have a chance that you have the white dwarf and another star, and then you find the mass by some other means. Okay, as you said that there could be other masses. I'll come to that.
Can you remind me what nu was again?
Nu was here. Let's see. Yeah. Okay, let me myself up. Did I go? Yeah. That is the way the nu comes up here. M tilde for spin up and M tilde prime for yeah, that's all. Okay, which depends on what is the J value you are going to take. Okay.
In this plot, the rho c is the density at the center.
Rho c is the center. Okay. So now this is basically the idea that there is a change in the mass of Chandrasekhar limit, which is potentially possible. And it's also related to the change of statistics, which plays a role. And whether how it affects our calculations on type 1a supernova is the question. Okay. Distance of type 1a supernova is actually for accumulation. Since peak luminosity is changed due to the change in the limit, we can expect, we have been measuring the distance incorrectly. It will be enhanced. This is what I think. As mentioned earlier, it's not only the peak luminosity, it is also how it declines. It is what is produced after the Chandrasekhar limit is exceeded. What is responsible for supernova for the explosion itself. So what is produced there, they play a role. And that decline is given by what is called a Phillips curve, which I have already done. But the basic thing is these things are very powerful luminous explosions of stars. And the light curve of type 1a supernova mostly depends on the crucial point is what is the amount of nickel that is produced during the majority of energy is through that kind of a thing. Nickel is the crucial responsible radioactive material, which is responsible for the spectrum which we analyze here, from where you consider the apparent luminosity and from where you consider what is the thing. This is basically the reaction. How much time I have? Okay, good. Okay, so the luminosity therefore depends directly on the mass of nickel produced, because this is one of the things. Because once you go into the details of computation and you want to look at how much change will be produced, we have to look into the nitty-gritty details of how that luminosity is produced, and that's one of the reasons we have taken this kind of thing. So in principle, there are other things also. So the relation is peak luminosity is given by some nickel mass in the white dwarf when the supernova takes place, and exponential of some time rise to the peak luminosity maximum, and the decay rate of this thing. Based on that, some models people have computed, which relates the nickel mass to the time for the decay of luminosity of the whole thing. This is also used whenever we want, we have to compare it with the curve which is there for luminosity, which is detailed calculations which are done. Okay, finally, the models predict luminosity due to 56 nickel as this kind of a number, which is relating m nickel to the solar mass. What is the ratio, which will depend on that. The crucial thing is we don't know what is the mass of the white dwarf. Since we don't know what is the mass of the white dwarf, and we don't know what is the real luminosity, we take by some kind of parameterization nickel mass as a responsible for the luminosity with some parameter which will determine what is the value it will go. So that is the first assumption. The peak luminosity is related to the mass of the super Chandrasekhar white dwarf. Unfortunately, we don't have a precise handle on this. For major cause of luminosity is due to the presence of radioactive. We don't care how much is the mass. We will worry about what is the nickel mass. The nickel mass can be computed from the spectral analysis which people have done, how much nickel is there. Okay, and from there they can, if you assume the formulas which I have given earlier, we can even expectation for the white dwarf mass also can be computed, and that is what gives you some kind of mass like 2.2, 2.4, 2.1 solar masses, which I'll give the example. But the basic idea is they are using this for estimating that. Okay, so we are going to revise this Hubble constant based on this. So I should tell you about the Hubble constant, and there is a formula which is used, which is called the trip formula, and I will give you how the trip formula comes up. The mass of 56 is known by the measurement of these overluminous this thing, and this is the so-called FLRW metric which is used for this thing, and the spatial part of the metric in Cartesian coordinate is the 3D Euclidean metric. The spatial distances between 2 points, this is meant for some of our students, is a t times chi, and d is the proper distance and chi is the co-moving distance, and the rate is essentially that a dot by a will determine this, and the h naught will be given by v by d, where v is d dot, is the recession velocity. Is more or less one page description of how the Hubble constant is obtained from FL or W metric. This is basically the idea. Okay. We will explain now Tripp's formula for Hubble's constant, where we use directly 56 nickel to estimate the Hubble constant. So the formula, which is Tripp formula, is log of H naught is given by MB minus small mb 52.38. Don't bother about these numbers. They are all, I have substituted them. This is the formula, where MB here and small mb are absolute and apparent magnitude of the peak, at the peak, the luminosities. The rest of them. Q naught is a deceleration parameter, which is actually a double dot by a dot square, and Z is the redshift. In the above, Z and MB are observed quantities. Here you have Z, which is there, and MB is also observed quantities, and the rest of them are from measurements. They are observed from measurements. The deceleration parameter is a constant depending on the choice of the cosmological model, which I have taken it to be a FRW metric, and that value is some 0.55. So you essentially substitute those things, you will get this 52.38, all those things. Yeah. So this is the thing. Now this formula, which is there after substituting that Q naught value, which is here, which is the 52.38 essentially come from log C or something like that. Okay. So the next is you substitute that definition of mu, which I had earlier, mu plus mu is equal to m minus m, that formula which I had. Essentially, I am substituting here in this equation instead of d. From there, this equation is simplified, and then I rearrange and then do this simplification. So I am explicitly giving the so-called Tripp formula for Hubble constant, worked out from the two numbers. Actually, numbers are, one is MB, which is magnitude which you are going to use, and the second is Z, which is a redshift. So this is the formula for Tripp formula. And the last one is that capital MB, we are going to use nickel mass for this, and then list, and then do a statistical analysis of estimating what is a new estimated Hubble constant from there. That's what is done. Okay. In this study, about 8 overluminous supernovae whose progenitors are thought to be super Chandrasekhar white dwarfs are analyzed, because these are the things which we have data, all the data about nickel mass and everything are there. Even though the number of super Chandrasekhar thing is of the order of 15 or 16, we do not have data for all of them. There is some confusion about that. So whatever is available, we have taken. So we estimate the Hubble constant is drawn up from using the Tripp formula. The relevant data for the 8 supernovae are given in this table, which I'm going to show. The analysis for the value of the Hubble's constant is presented in the following section. After that, I'm going to do a chi-square analysis using these 8 numbers. And then from there, I look for what is the likelihood probability function where it reaches the maximum value. This is what I'm going to do. Okay, so these are the table, and the name of the supernovae are written down here, and these numbers 2003, 2006, these are all the year in which they were discovered, and the Z values are here. MB values are given in the table which they have produced, all experiments, and this MYD, this is actually what is given, and this white dwarf mass, as you said, you can see some of the 2.12 are there. They are estimated from formulae, from nickel mass itself. So this is the kind of expectation which you have. Obviously, they are exceeding the Chandrasekhar limit. All of them are exceeding the Chandrasekhar limit. Okay. Yeah. There is a theory which they have developed on this thing and then compute. some astrophysics theory of that. But that part I'm not using. I'm only using nickel mass itself. I'm only giving those numbers to say that they are really, well, it should be expected because nickel mass itself is very close to Chandrasekhar or above Chandrasekhar. So if a subset is of that thing, the white dwarf mass is expected to be much more. That's what is the thing. Okay. The likelihood function, how do I do that calculation? The likelihood function is trip formula. What I'm going to assume is, I will assume the Hubble constant to be some value between 60 to 80. That will give me in that formula certain apparent, the MB, which you expect from that formula. Now you do that for each of the supernova, and from there, okay, the absolute magnitude is a quantity derived from the amount of nickel produced this thing. So we derive the value for the Hubble constant using the data from these things. So what is done here is, I define chi square, this MBI minus MT, where the mass expected from trip formula for this thing, assuming that is a thing, and then chi square, and then take the product of these things, exponential chi square by 2 divided by normalization factor, and take the product of pi and consider this function L. Okay, so this L is for all the supernovae, but particular value of the Hubble constant, it will be between 60 to 80. Now you use for all this number the probability of this thing and then plot it. Find out where it is maximum. Okay, find out that is the most likelihood value you expect for this, using this thing from the background of this theory which is there. The graph shows that the joint likelihood function plotted against different values of H0. The mean of the distribution which is obtained is 68.686 kilometers per second per megaparsec. This value we get, and the standard deviation is something like this. Therefore, from the data over luminosity, we get a value. This is the kind of thing which is there, and this is the likelihood function which I have given you how it is estimated. This is the thing you repeat chi square. You find out the value of MT for each of the supernova, assuming that is a mass trip formula, and then how far it is away from that maximum value, because other things are also contributing. From there you compute this probability function, and from there you find out the most likelihood thing from this function L. You plot this for different values from 60 to 80 and find out what is the maximum, where it reaches maximum value. Likelihood function, Hubble constant, this is the revised value which we can claim is 68.6. Okay, this is the value which looks little satisfactory for us because it is going as expected. If the Chandrasekhar limit is exceeded, the distance we have been measuring incorrectly, and the distance measurement, if it is more than what we were usually claiming, the Hubble constant will be reduced from 74. It comes to this kind of a number. This is what is the, yes, 10 minutes. No, I don't have that much to say. Okay, so this is the thing. So to conclude, some references. Our super Chandrasekhar limiting mass white dwarfs as emergent phenomena using non-commutative fuzzy sphere. This is the reference. Natural evidence for fuzzy sphere non-commutative geometry is in this paper. Third, significantly super Chandrasekhar mass limit. I have given only archival number. They are all published. You don't have to doubt that part. It's all published. It's easier to give the archive number and go with that. The last one is what we have done now. The last one is what I have shown here using the nickel mass, trip formula, and likelihood thing, and the so-called Philip curve, etc. All those data, using that, we have estimated, and that work is done with Abhinandan Ravi and Surajit Kalita. Yes, this work was done in collaboration with Abhinandan Ravi. He is a visiting student at IMSc now. Is visiting me. Surajit Kalita is a postdoc at Warsaw, And the preliminary ideas were presented at conference on classical and quantum gravity about 4 months back in November. Naresh Dadic's 80th birthday was celebrated in Cochin. So they invited me. Then I didn't have this much details of calculations, but it was intended more to felicitate him. So I gave the ideas which were there, and the calculations were now. We are almost ready to write the paper. It will go on for some more time. Within a month, it will come. And I thank specifically Ravi Sheth of University of Pennsylvania for discussions at ICP. And many of his remarks and discussions led to my rethinking on whether it can be utilized. I was more interested in fuzzy geometry and white dwarf, more like a theoretical thing. We never bother about experimental thing, but I thought, why not do it? So this is the calculations which led to all that. And thank you.
We have some time for questions.
Yeah, I have a question regarding this strip formula. How do one notate this formula?
Well, I actually gave the derivation of the strip formula. Strip formula is not very difficult to derive. This is one of the things.
But what are the conjectures and assumptions based
No,
on
it's
which?
a FRW metric is what is used. So what it uses is what is done is there is the star, white dwarf, and the light is coming to us, and the metric is FRW metric. Find the geodesic distance. You find the geodesic distance, compute it. That's all that is there. And this part of the calculation which I have given here, this equation 22, is there in Weinberg's book. In detail, it is there. After that, we have to substitute for the values of our parameters here. First of all, this number which is there, I have to multiply by 10 power 6 because I'm not dealing with megaparsec. I have to deal it with parsec. That's why the 10 power 6 comes. The next is that mu and definition of mu, the distance. In our standardized way of writing, that is what is used. And then only logarithm, following that simplifications, very straightforward simplification.
Okay, thank
This
you.
is one of the things which I can do it. Yes. Yeah.
So, yeah, I'll go ahead. So, the algebra that you had for non-commutative geometry, does it uniquely follow, I mean, from non-commutative geometry, or can you get multiple algebras?
That is only a model. Okay. As I said, this is a model. Generically, non-commutative geometric models lead to a change in statistics. That is a basic principle. Ball and many of us, we have been playing with that for earlier, but most of the time it is theoretical work. That statistics can be changed, can we verify that experimentally, various places, etc. People have been talking about, he has been talking about, and we have been talking about. So only thing is we have to do a calculation, computation. When you want to do the computation, we need some kind of a free particle or particle on the surface of a sphere, all those things, which will be easy to compute. And that's why we took the sphere. And when you take sphere, you go next to a fuzzy sphere. Sphere will lead to Chandrasekhar limit. Continuous sphere will lead to Chandrasekhar limit. That's what is that. Because there's a spherically symmetric.
So also, quick follow-up on that. Are there any free parameters in that, and how do we fix it?
The free parameter there is what is the value of the J, because our xi are angular momentum generators. That angular momentum generators will be 2j plus 1 cross 2j plus 1 matrices. That J is a free parameter which I have to. That will have L. That's what we call L. And from there, M value will be from minus L to plus A. So the new max which I used that number. So that free parameter is only that much.
Yeah. So you seem to be assuming that there is a change in the commutation relations at about 1 Fermi. At about 1 Fermi.
But not about 1 Fermi. Before 1 Fermi,
yeah.
From 10 power minus 10 to 10 power minus 13,
yeah.
in between,
Okay.
the things are put. See, the thing is the distance between the electrons become closer than Compton wavelength.
Yeah.
So that leads to certain parametric, which looks like magnetic field, incidentally, where quantum Hall effect also gives a.
In that case, wouldn't you see some effect in ordinary high energy physics? Because that's
Where?
in like high energy physics experiments.
No, they always deal with much more than Compton wavelengths. They don't go to the Compton wavelength scales at all of the electron. So, but for the new, for
Even for SAT, like one thing you could imagine is that because there is so many particles,
Hmm.
there is maybe the physics is a little bit different. But even such high chemical potential things, I think, would be accessible in things like that.
it's probably possible. I'm not saying it is not this thing. Most of the times, we have been talking wherever we have been talking about statistics. We have stayed above the Compton wavelength scales. That's the point.
No, also here you have a bunch of particles, right?
Yeah, yeah, large number of them also.
That's what it's like.
Yeah.
For instance, when you have people say that
Yeah, in principle there. Yeah, I agree that Rick and other things, but they are all going to nuclear physics areas where about neutrons, protons, etc. Their Compton wavelength is much smaller.
No, not only that. Central region, the central gravity region,
Mm.
they have bosons. They don't have photons.
Mm.
Because all these
So what?
colors.
It's possible. I have not thought about using it in particle physics.
Any question in the back?
Yeah, particularly the students.
Yeah.
DRG, shouldn't you look at the Dirac equation
I did.
rather than the
I did use Dirac equation. After I gave the Laplacian just to motivate, to tell the students the Laplacian here. After that, I went to Dirac operator. So I went to Dirac operator because if I start Dirac operator with this thing, I have to explain that.
Yeah.
So it's easier to explain a Laplacian than this.
Yeah, I have a quick
Yeah.
question. You have a ratio B by BC there.
Yeah.
Do you have an idea of how big that is?
We do we have written the paper. I don't remember offhand.
Well, yeah, this number.
This
B by
number.
BC in equation 12.
Yeah, we do have in our paper, it is there. This BC is what is called Schwinger limit, which is there for all these things. And B is the value which comes from this computation which we have done.
So let me ask another question. Is it smaller than 1 or
Which one?
B by BC?
The B is less than BC. B is less than BC. It cannot go to BC because something will happen when go to the Schwinger limit. So B is definitely less than BC. There is no problem. I don't remember often what was the value for the new B. Actually, what is important in new B? What is the value? I have to check that.
It's not obvious, but maybe that you're maintaining full SO3 rotational, right?
Yeah, yeah.
You are?
Yeah, I'm maintaining that.
How is that? Because you're squashing your sphere. No?
I do squash the thing, but squashing is arbitrarily, I'm doing it. Essentially, it gives me the degeneracy between minus L to plus L. But at the end of large N limit, okay, they all become so close that it is really, it doesn't really matter at that level. Squashing is done only to achieve this. As he said, I could have introduced a parameter. Huh? That level. At this.
Not the same as when you use the non-commutative model.
I use the non-commutative model. It is true.
Arrive at this, but
So that's why I'm getting something in terms of some magnetic field artificially created, which is in some direction, and then the whole program is with respect to that. That's what it looks like that.
So what you do is instead of looking at the microscopic degrees of freedom, you are parameterizing it using your fuzzy sphere. Many
Yeah.
things can lead to this modification.
Essentially, there is an effective magnetic field in some direction which is high, and that is the.
That is what Manjari showed in her. She turns on the magnetic field and they can explain these greater than 1.4 solar mass.
She did. I don't know. I didn't know about
And I
that.
was there in the students' DC meetings.
I see. I didn't know about that. But this.
2.2 something.
Yeah, it is there. The point is, it is there. The only thing is whether we can understand it in some way, and this is one of the.
sort of conventional physics. Conventional physics explains that for whatever reason there is a high magnetic field. Once there is a high magnetic field, you can change the dispersion relations, which in the end lead to doing the.
That's what I'm saying. So this is a generic thing. So many things can change the dispersion relation.
he wants to.
Dispersion relation, you get
Yes.
the kind of result that you get.
So, what is the take-home message here? It is you are solving the Hubble Tension problem, or it is changing the Chandrasekhar limit? So, what is the
Take home message is Chandrasekhar limit was already changed by 4 years back in our paper and many other people's papers. Chandrasekhar limit. The take home message is it is related to Chandrasekhar limit change, enhancement leads to more the luminosity being measured by the mass of the thing, and it gets enhanced. That enhances the distance. We have been measuring it incorrectly. We have called the distance of the supernovae from us a particular value which was earlier number that has to be increased. When you increase the number, Hubble constant value comes down from 74 to some 68. That's all the take home message.
Is there some way in which your model tells that you can increase the limit of the modification of Chandrasekhar limit up to 2.4 and go further? Can you predict that you will not find
It is there. 2.4 is the maximum. In fact, that graph actually leads to, like Chandrasekhar when he came to 1.4, our limit also 2.4 is the maximum. It is also the maximum. So it is there. The graph actually comes to zero radius, like the way Chandrasekhar's curve also comes to zero radius. That's a thing. So that's a maximum.
you are predicting that there is nothing?
Yeah, it cannot go. So we also predict earlier up.
Direct mass measurements of those by white dwarfs, right? So you are predicting that they will never see anything.
They will never go beyond 2.4. Yeah.
So I mean, just clarification that, I mean, that's independent of the algebra you take that comes out of commutative geometry, or that's dependent on the
That depends on the non-commutative geometry model I have taken. So if there is another model, it leads to something else. They have to worry about how to explain that. If there is an explanation. There is a limit.
They have a prediction in their model.
Yeah.
Yeah, that's also.
Yeah,
Any
it is there.
questions
2
on
point.
that?
That was there about 4 years back. It's not new
You must
because
have
that paper is
studied
there.
Chandrasekhar limit in your statistical mechanics course.
Now they are wondering what they will write in the exam, whether they will write 1.4 or 2.4.
No, 1.4 with the Fermi
1.4 is
statistics.
safer.
1.4 with Fermi statistics is okay. Yes. And free electron gas.
So you said that it changes statistics, but you only use the result in the dispersion relation.
Yeah.
So like if I
That gives me the dispersion relation because it's all free electrons.
suppose I just change to fermions, interchange to fermions. So how does
The effect of the statistic change is effectively built into the spectrum of the Dirac operator. And after that, for me, it is only a Hamiltonian whose eigenvalues are given. I fill up that thing with many electrons. One by one, I put everywhere. Do the partition function. That's all.
my question is separate. It's in the context of statistics. So like you mentioned in the beginning that when you interchange boson, the theta factor is 0 and for fermions it is 1 pi. And with this non-commutative thing, it is different. I'm just asking how does it change? Like from between 0 and pi, how does it?
That will depend on that value nu b which I have given. It will depend on how many electrons, the total number of density of electrons, and also the J value which I have fixed up. All those things, it will depend on that. It will depend on that. Incidentally, there was some calculation by Biswajit Chakraborty long back where he considered ideal fermion gas modified by the new statistics, and like Patria's book, which gives the repulsion, effective repulsive potential between Fermi particles when you do statistical mechanics. There is a revision of that using different statistics. That's what he has done. So it's more or less close to that. But it's only relativistic. He was doing non-relativistic.
All right, a lot of questions. So let's thank the speaker once again.
Thank you.